Hello, can you guys hear me?
Hi, Mamoon. I was in the wrong meeting, I guess.
Yeah, I was wondering who is going to moderate the meeting. So good that you're gonna do that, right?
Yep. I'm the moderator.
Okay. I'm just sharing my screen, but can you hear me all right?
Oh, yeah.
Okay.
All right, so we're at the start time today. I'm the moderator for this presentation, and Mamoon is going to be talking about design, construction, and operations of a dam. So Mamoon has 25 years of experience in geotechnical, geoenvironmental, and infrastructure engineering at Tetra Tech, and he's led multidisciplinary and multi-stakeholder teams that deliver complex and challenging design and construction projects. His areas of expertise include design and construction of embankments, dams, and waste dumps, dam safety management for water, hydropower, and mining, risk assessment, regulatory compliance, tailings management, large-scale site investigations and foundation characterizations, instrumentation programs, as well as laboratory and in situ testing. So Mamoon currently works as director and principal consultant of dam practices for Tetra Tech Canada, and he's the secretary treasurer for the Canadian Dam Association, CDA. Maroon also chairs technical committees, working groups, and organizes workshops and conferences for CDA, tailings, and mine waste, and the Canadian Geotechnical Society. Maroon is an instructor of CDA technical workshops, and he's a member of Technical Independent Review Boards, ITRB, for mining dam projects, and acts as engineer of record for mining dams. So let's welcome Maroon. Thanks for doing this.
Yeah, thank you. All right, guys, thanks for inviting me to give this talk. So before I go into the details of my presentation, I just wanted to acknowledge, as you heard from my the introduction, that I am heavily involved with the Canadian Dam Association, and we provide um, several training courses. And I took some content from some of our courses that are relevant for this webinar. All right, so before I get into the presentation, I will just briefly talk about my organization that supports me. So Tetra Tech is a multinational company, and we have thousands of people, and they work in 7 continents and 125 countries. And it's a engineering and science company, and we have offices predominantly in the North America, but as well as in Europe, Australia, and South America. In terms of the dam engineering, in our Canadian base, our services include design, construction, analysis, and dam safety work in general. We have offices in several locations that has, we actually have more than 50 offices, but I think these are we have a dam focused team in British Columbia, Alberta, Manitoba, Ontario, Quebec, Newfoundland, and the northern Canada, Northwest Territory, and Yukon. And we provide a client-focused approach, resulting in long-term and low-maintenance solution for dam. I think Tetra Tech is working on the dam industry across Canada and internationally almost over 50 years now. So a brief outline of my presentation today. I try to touch on some general understanding of the dam. I assume most of you guys are like young professionals, so you may or may not have exposure to dam. So I'll touch on some of the fundamentals, which we call Dam 101. We actually have a course through CDA, which we have provided in the past, and we're currently revising the content, so we'll provide those in future. And then I'm gonna provide a brief overview of how the dam industry looks like in Canada. And then I will get into the main aspect of this webinar, that overview of dam projects from the concept to construction and operations. So um, dam, I think, is a complex structure, but there is so many things to talk, but I will keep things very high level in general, so that you guys can get a bigger picture than like nitty-gritty detail of any content that I'm going to discuss. So the what is dam? Then dam 101 I'm going to cover why we need dam. It's also important and what are the key features of a dam and do they fail? Um, so getting into that, I think this is one of the large dam in Canada. It's a WC Bannett Dam in BC Hydro. I have a lot of photos from for the dam in general, and a lot of this dam I had an opportunity to either work or visit. And some of them are generally uh, known dam, I think, across the world. Um, so what is a dam? So by definition, I think we have a specific definition in Canada, what is the dam, but then we also have a definition for different jurisdictions, I think, because dams are regulated by the province. Although we have some federally owned dam, but there is no federal legislation or anything. So, anyways, in general, I think it's a barrier or retention structure that retains water. That's one of the main material that it contains. But then it goes beyond that. I think water containing substances, and you will see some examples, and then sometimes fluid waste that come out from industry. So we have a significant retention structure for those type of fluid waste as well. And finally, I think the tailings, which is a byproduct of the mining process. So dam actually go beyond just the conventional water dam. I wanted to briefly touch about the history and evolution of dam because it's important to understand actually how does dam fits into the progress of the civilization. That way you get an idea actually um, how complexity of the dam and its usefulness and etc. So the recorded history shows that the as early as 3,000 years ago, but we do see dams over the last 2,500 years, I think, in Europe as well as in Asia. They use the locally sourced material. For example, in Egypt or by the Romans, they had mostly built rockfill dams. And then in the Asia, they were more on the earthfill dams. But the actual modern dam construction, which we see now, began in 1850s and onward, because that's when I think the civil engineering discipline started to take shape. And then we understood more about soil stabilization, foundation, and etc. And since 1850s to the 1910, there was a major advances in concrete dam, predominantly in French and by the British engineers. But then from 1900 onward, around 19 first decade of the 1900, I think USBR, United States Bureau of Reclamation, I think they started a major organization, and then the dam across the continent. And then in Canada also same time, I think we have started building significant dams. And then I think the main dam building era that in my view is actually post-World War between 50s, 60s, 70s. I think that's when increasingly industrial development and then all these countries was developing in Europe and North America. To support that development, I think there was we need a lot of energy, and hydropower particularly was dominating lots of dam construction. As well as I think post-World War, there was also a surge in the demand for commodities and metals, and that also flourished the mining industry. And mining industry in a traditional mining process, they produce a lot of mining residues, right? So we call them tailings, and those are more like semi-solid, semi-liquid material, and they need a containment. So some of the larger, dams was constructed to support those mining. And over the last 2, 3 decades, I think we started to see less large scale dams construction in Europe and North America, but it actually shifted more to Asia, Africa, and then also in South America because they are developing rapidly in different parts of those continents, and they need a lot of energy as well as metals and all these things. So a lot of the large dam construction is actually happening in those parts of the world now. So why we need them? Of course, as I said, the hydroelectricity, right? But it's amazing to know that, still 60% of the Canada total energy comes from the electricity generation. And Canada is the third largest producer of hydroelectricity in the world. So you will see actually how I have a slide on it, and you will see how this dam and the hydroelectricity industry is actually spread out across Canada. But I think worldwide, I think still one of the major dam construction and some of the larger projects is around hydroelectricity and power generation. And the second place is the infrastructure, right? So a lot of these municipalities or the larger parts of the uh, country or district, they actually need to establish a permanent water supply and irrigation, as well as, we are having more and more houses in floodplains and etc. So we need flood control dam. So that's another big need for the dam. And then the third area is the more like smaller municipalities. They also need dams for, again, recreation, flood control, sewage lagoon, debris management, as well as water supply. In addition to those, I think some of the other industries, for example, I did a project for the Miller Western Forest Products. They basically lumber processing, I think, but they do produce lots of sludge. So they need a containment facility. So their facility is relatively high. So that classifies as a dam. And a lot of chemical plants or fertilizer, or pesticide, they do need to store their industrial byproduct or material that can be stacked. Excuse me. So that's another area. And finally, the mining industry, as I said, for the tailings, which is a mining residue. But in addition to the mining projects, if you guys are familiar, is relatively quite large. And some of these mining facility could be very, very large. Like where I live in Alberta, we have some of the largest tailings facilities, which I'll show some example of that. Some are probably 4 kilometer by 5 kilometer in the order. So that's a huge containment structure or impoundment structure. But in addition to that, they also need a water dam. So the mining site could be a combination of tailings dam, which either constructed by tailings and or constructed by overburden material or material from bottom, but predominantly contain tailings. And then they also need the water retention dam. For example, these two photos is one of the sites that I'm engineer of record in northern part of the Canada. On the left side, it's a tailings pond. It's roughly 1.2 kilometer diameter, and then on the right side, it's a water retention dam, and so that they have to create those barriers for the overall site, water balance and control purposes. So what are the types of dams? Dam could be of many types, but predominantly you will see a lot of earth-filled dams, either filled out with clay or sandy type material or rock-filled material. And then the other branches of dam are the concrete dam. And then in the concrete dam, that could be either gravity dam, where you have a massive, downstream part of the dam that acts as the supporting structure, or you can have an arch dam, or you can have a buttress dam. Now, in the variation we see mostly in the water dam industry, because that's where you can have earth-filled dam on concrete dam, because these are very large structure, and then they're always constructed with borrowed material or outsourced material. But in the mining industry, almost always are earth dam. I never really saw any concrete dams that are being used for mining. There might be some in some parts of the world that I haven't been able to work or explore yet, but it's always because you have either lots of excavated material that come out from the mining, or you have to use some source borrowed material. So that's kind of the bigger picture of the dam. And I think before I move into further, just wanted to quickly go over, okay, if you are familiar with the dam, wanted to learn more about dam, I think that's where you should start. So this is just a typical sketch of a dam. And you can see the top is the crest, and we use the word like downstream and upstream. It's more like coming from the river hydrology type environment, but ideally dam started from damming the river. So we use that type of terminology. So downstream means the outside of face of the dam, right? And then the upstream is the inside phase where the water abates. And then we call the both sides, abatement, right abatement and left abatement. We always look from towards downstream. And then there will be some ancillary structure. For example, we need to put a outlet at the low level so that we can control and water flow, right? Because sometimes if it is an irrigation facility, then you have to be able to, release water at a certain rate so that it acts as a water. Same thing. And then sometimes it uses a water intake. So we build this intake structure within the facility. And then for the flood control or the level control for the facility or emergency situation, we have to construct a spillway at some part of the dam, or sometimes you put it on outside the dam. The idea is that if there is a big surge of water or the water level rise, we'll let the water pass through that spillway safely, and that will prevent the overtopping of the facility. Because technically, as soon as the containment of the facility is lost, the facility is actually lost in all intents and purposes. So for the dam, always the intent is that under any condition, the contained material remain contained. It does not overtop. So that's why we have to come up with different processes, spillways, outlets, and etc. So the how dam fails, I think the bigger part of the dam practice is that we have to prevent failure of dam, because dams are massive structure, and consequence of failure could be detrimental, right? It can cause fatalities, and in a big number of fatalities we have seen throughout the history. So um, so by definition, as I said, any uncontrolled release of the reservoir or loss of function of the facility would consider as a failure. Now, there are predominantly three key failure modes. Either, we can lose the control of the reservoir level, so it will overtop. And as you can see, like an example, a failure happened in Michigan back in 2020, where they had a flood and they lost the control. Spiller didn't work, and the dam overtopped and started to fail, right? And then the other thing is collapse. Collapse means like the actual dam structure. Either there are some weakness or structural issues or seepage issues or foundation issues. The facility itself, the dam itself actually starts to collapse. And and then first the dam collapses, and then it loses the containment. This is one of the recent failure happened in Brazil, one of the mining industry that's actually caused somewhere above 200 fatalities. So it's a major recent catastrophic failure that we have observed. Now, in terms of the dams in Canada, Canada is actually one of the prominent dam building nation, and dam helps to meet our economic and social need. And but I think the interesting thing in Canada is that Canada is a large country, and our climate and topography quite varied. I think in terms of constructing and operating dam, right? We have uh, high mountain, we have flat prairies, right? And then we have like shallow um, uh, landscape. So there's a lot of variation, right? Where I live in Alberta, and versus what for British Columbia or Quebec, I think we see that we use the advantage of topography and we build our dam. And then of course the climate is a big issue in terms of the seasonality, because that affects how long it's going to be constructed, what construction methods are going to be used, etc., etc. So CDA did a inventory a few years ago. I mean, we don't have a very formal tracking of dam inventory in Canada. CDA did one formal one back in 2019 when we had a international congress conference actually in Canada. So our estimate is in general there are over 15,000 dams in Canada combined, all sorts of dam, water dam, mining dam, industrial dam, and etc. And we over 1,150 plus large dam. Large dam definition is set by the International Commission on Large Dam. It's like any dam that is over 50 meter and has a certain amount of volume. So, and again, as I said, the dams are owned by federal government and then also mostly provincial government, but then we also dam owned by electrical utilities, industrial and mining companies, irrigation district, municipals, and private individual, because a lot of the farmers also are like a smaller operators. They do have their own dams as well. So we have a significant number of dam in Canada. Now, in terms of the job market or the industry, again, there is no formal tracking of the job market, but I did a quick search on hydropower industry is a little bit more organized, and the data that I found, it shows that there could be as much as 140,000 direct and indirect jobs in the hydropower industry. It's a bit trickier for the mining industry, but can get a sense, right? There is over 420,000 people work in the mining industry, right? And 274 jobs supported indirectly. So it's almost like 750. Now, even if we take 0.05% of them work in dam industry, that's around 5,000. So there is a pretty good number of people actually work in the mining dam industry, and it's growing. So as you can see that it's a pretty important, job sector for the civil engineers particularly, but also for the other disciplines. And I will explain why that is. So again, going before I move on the Canadian landscape. So the most dam we have is actually in Quebec, like number one. They got these are the large dam, but there are more dams, I think, that are not as large. But in terms of large dam inventory, we have over 600 large dam in Quebec. And I think hydropower, as most of you know, that is their main source of energy. So it's pretty big there. And then I think the second one would be the Ontario. They also got over 100 large dam, and hydropower again is a big industry for them. Third one is the British Columbia. They also get close to 95, close to 100 dam. And then the fourth is the Newfoundland and Labrador, around 85 dam. This inventory is until 2019, so that would be more now. And then the rest of the part of the country, like for example in Alberta, we are not hydropower is not one of the main energy sources, but we do provide irrigation, recreation, and water supply, and drought and flood management. So we have a decent number of dams as well. So that's kind of the bigger picture. So you guys can kind of get a sense of, if you wanted to do for hydropower dam, which province and which part of the country you wanted to relocate. And then I think on the mining side, again, I think there isn't really a formal database, but I think one of my junior friend, Nahian, actually started to pull together like an inventory for the mining dams across the world. So as a part of his data set, he looked at the dam inventory in mining dam inventory in Canada. You can see he geolocated them. So there's quite a bit of concentration in British Columbia, some in Alberta, and then Saskatchewan, and then also in the Ontario. And then we also have some in the northern Canada. So around 800 dams. My hunch is that there might be more because they're not always reported or etc. So it's a pretty significant number as well. And lastly, how good we are in Canada in terms of dam safety. I think we are one of the leader in the world, I think, with respect to promoting the safety of dam. And we have the Canadian Dam Association, we have the dam safety guideline, and etc. And but I think in general we had a very few dam failure resulting in loss of life, because with respect to the failure of dam, what's important is whether, of course, environmental, social aspect is also very relevant, but loss of life is all sometimes makes headlines and more important. So we have 15 records of dam failure resulting in 38 lives lost, and earliest record is 1843, and largest single event is 5 lives lost in Ontario. And Quebec. Now, if you guys are in the dam industry or keep an eye, one of the recent failures that we had that made a worldwide news is the Mount Poly Dam failure. It's a tailings facility in British Columbia. It supports a copper and gold mine, and there was a 17 million, a million meter cube of water and 8 millimeter cube of tailings material was lost. There was no loss of life, but there was damage to the nearby water bodies and the environment. So this, as you can see, this is almost like a ring dike, ring facility, and then there was a tailings dam across the uh, three sides of the facility, and then this is where it fails. And if you look at it from downstream towards upstream, that's the picture you will see. So there is a breach over here, and that lets all the fluid and everything released. So it was a quite significant failure, and that led to change in regulations and safety practice and etc. in British Columbia, and lots of awareness on the dam safety across Canada and worldwide. Anyways, we still do build large dams in Canada or big projects, I think. One of the most recent one is the Site C Dam in British Columbia. They have been constructing it for last probably 10 years, and the project cost probably was in the order of 16 billion. It was commissioned actually earlier this year. And then another one in the Muscat Falls Dam in Newfoundland and Labrador, which was commissioned in 2020. It's also a massive facility. And then the one close to my home is the Springbank Office-Stream Reservoir. I'll share a bit more information about that. And the Alberta government constructing it for last 4 years or so, and it's also been getting to completion. It's almost like a $1 billion project. And all right, so how does so the dam projects, right? So the next part that I'm going to elaborate is the dam projects. How do they look like, their life stages, and etc. So these are complex, multidisciplinary, multi-stakeholder, and sometimes lengthy and big budget, right? And it involves all major disciplines of engineering, as well as and science, as well as commerce, because these days dam projects. I mean, you guys are, I'm assuming, all are geotechnical engineer or geological engineer. I mean, we do have a big part in the design, construction, operation of dam, but as you can see, pretty much all major disciplines, um, civil, hydrogeologist, hydrologist, geoscientist, mechanical, electrical, process, biologist, economist, environmental engineer, and the automation, GIS, computer science, and then geochemist. There are probably more that I haven't listed here. So in a DEM project, you actually need all these disciplines. So the reason I wanted to highlight that, going to work in the dev industry, you will have also be exposed to other, that's what I think I find more uh, value and challenging, to bring our knowledge and pair those with others and solve the difficult problem. And also, if you wanted to do a dam project, then the stakeholders are also important, because it's not that the engineers and the owners can just get a dam project up and running. It needs a lot of engagement with the regulator, owners, the landowners, I mean, and particularly in Canada, right holders like our First Nations and all the other important stakeholders. So we need to work with them very collaboratively. So it's science, engineering, but as well as it goes beyond that, right? It needs a lot of engagement and etc. Um, so the project, dam projects, I think it goes through a pretty elaborate life stages. So starting from what we call the pre-feasibility study, I'm going to elaborate each of these boxes a little bit with some practical examples that I was involved in, so that I can give you guys a little bit more details. The project usually do like these three stages: pre-feasibility, feasibility, detailed design. So these are all like when things have not been constructed, right? All the front end work that we have to do, all the details with respect to understanding the site and meeting all the requirements, right? So that could take upwards of 10 years, 2 to 10 years, because given the complexity of the project and the stages is required, and the level of details we need in every stage, it could be quite lengthy process. And then comes the construction and commissioning. So once we get all the design and everything ready, then we start construction, which can also take, somewhere between 1 to 10 years, because if you are building a small dam like 100-meter long, and you can probably do it in a season, but if you do a dam in an environment, that a complex one, it might need a couple of years, and sometimes it may need as much as 10 years or so. And then the last part is, of course, the operations, repair, rehabilitation, and decommissioning. Like once dam is commissioned, then we have to operate it. Like water dam, we operate for hundreds of 100 years or so, or more, I think, and unless and until there is a reason for to decommission that dam for whatever reasons. Um, and then, but I think throughout this process, usually most dam need some repair and sometimes need some major rehabilitation. I say 10 years because you might say, okay, we kind of dam needs 10 years. So these are more like on the mining dams, right? Most of the mining projects, mine life is probably 10 years, 15 years. So that's when they operate the facility. But after that, they move into closure or decommissioning phase. So so that's why I think, depending on what type of dam you are building, the operating life could be order of 10 years to 100 plus years. Okay, so now I'm going to, rest of the part of the presentation is basically just diving in a little bit for each of the phases and provide some examples. I'm going to provide 2 examples for every stages, one for the water dam, one for the mining dam, so that you guys can see the subtle differences that we had to capture in these 2 types of dam. So pre-feasibility level, one of the important thing is that, where are you going to build the dam, right? Usually we have to select that suitable location. And then if we find the location, then how much, whether do we need any field investigation? It could be limited to just site visit because it's a very preliminary stage, or it could be more like, a desktop study. But usually in the feasibility level stage, we do a lot of desktop study to develop the concept. And in most cases, we developed options for the client because at this stage, you don't have a lot of details to pinpoint your facility, right? So it's almost like, in the pre-feasibility level, you start with a very big area, right? Like in a land area, I'm saying, and then you study that area before you move into feasibility stage where you started to narrow down if you are building, because let's say it's a flood control project, right? So there could be more things than just building a dam. We as a dam engineer will go and look at just from the dam aspect of it and try to identify where we need to put our dam, right? So that would be our pre-feasibility. And then once we find out few places, then in the feasibility level, we're going to look into those stages before we go to the detailed design for one particular location. So it's a decreasing size of the project area. So an example that I had the opportunity to involve, like it's in Calgary, that's where I live. And this is the area between Calgary and west of Calgary, right? This is this zoom in of that area. So we have this Bow River water basin. And a lot of you guys might recall that we have a big flood in Calgary in 2013. And then in that flood, I think the Calgary, the area nearby the Bow River and Albo River was flooded, and then we had damages in the order of several $billion, right? So subsequent to that, I think Alberta government has commissioned a study, and there was a number of facilities that was identified to be constructed. So that was one driver, as well as where Alberta is a prairie province, so southern Alberta has a huge irrigation and the agriculture industry. So we have to control and manage the water, as well as because of various reasons we also have drought. So they divide this project to balance the water supply and to manage the flood and drought. So so then I think one of the requirement for this part was that to identify where we need to build some water retention structure. Because this overall project will need some dams to construct to divert or manage the water or store water. So this green highlighted area in between Calgary and Canmore was selected suitable location to have a dam. So that's what was studied in that pre-feasibility level design. And then I think that zoom in area that I showed, the study they did some geological review, environmental and social aspect in a bigger scale, indigenous stakeholder and the other stakeholders. They identified the regulatory issues, and they did a high level cost estimate for the three options that were selected at that stage. And likewise, I think I was involved in a tailings facility. If you look into Alberta map, this northern area near Fort McMurray, Alberta, we had a large oil sands mining industry. So one of the things that we need for them is to build a tailings facility, which we call the tailings deposition area. So this particular facility is called out of pit tailings area. So at this stage, what happened is that they provided us the mine plan, tailings plan, and they looked at the high level project uh, uh, um, complexity and then the project dynamics and project economics and all these things. And then they figured out, okay, you see this purple area, that's the boundary of the mine site. So the area that's where they have the ore, they are going to use those area for pit construction and etc. But they identified the area where they're going to build the dam. So we looked at it and we know that how much tailings is going to come and how the mining is going to develop. So we take that information, we develop the preliminary concept of the facility. So that was the outcome of this pre-feasibility design. So now moving on to the feasibility level design. So what we do, so now we started to look into the site because we have to confirm the site at this stage. We really need to pinpoint, okay, which are the area that is most suitable for the locating the dam. And then at this stage, we definitely need to go to the site, do some investigation, uh, budget permitting, but we definitely need to collect some site-specific information to do some site-specific studies and to develop the preliminary level design. It could be 50% plus minus in terms of cost estimate or 25% plus minus depending on the project and how the project is broken down, the time scale and the complexity. But we definitely need to start to look into the some level of details. So in a nutshell, I think what happens is that in terms of the area, like in the pre-feasibility, feasibility detailed, we narrow down from bigger area to smaller area. But in terms of detail, as we're narrowing down into smaller area, the level of details that we look at will increase for that particular area with respect to constructing a dam. So going back to the same example that I provided, so we're involved in this pre-feasibility design. Our team was the geotechnical lead for this project. So we did investigation, and then the other partners in the team, they looked into the reservoir area design, because as soon as you load the valley with water, the valley water and everything will, become saturated. And depending on the geological condition of those area, there might be some instability and all these things. So we need to study that. And then we have to engage. We have to effectively engage with the stakeholders, get the permission, and go there and drill, right? So the outcome was that once this preliminary level details was developed, we could see much more closely compared to the pre-feasibility each of these options, right? And we were able to come up with all the relevant information for the owner to select a preferred option that is going to move into the detailed design. Likewise, the feasibility design that we did for this project was that once in the pre-feasibility, we identified the boundary, we identified what kind of dam. We started to develop those dam, right? We come up with this dam shell. Basically, we know that in this area we will need two different cells, and each of these cells, their dimensions, and then how high the dam going to be, what is the preliminary design. We did geotechnical modeling, surface water modeling, groundwater modeling, because as I said, these facilities are huge, right? This was particularly probably 4 to 5 kilometers by 4 to 5 kilometers. So it's a very large area. So it's going to affect the local groundwater, local surface water, in addition to our geotechnical, aspect. And we need to study the whole thing, right? That was part of the feasibility design, and so that we got all the information we need to develop. So these projects are really truly multidisciplinary, and I have to work very closely. We meet every week, and then every 2, 3 months we have a workshop. We go through the details, and then we present to the review board. They provided their comments, and we go back. So it's a pretty detailed work happened over a year or two. I forget the exact timeline. So, and then we develop the cross sections of the dam and etc. so that we can provide the cost estimate and scheduling, right? So then we go to the detailed design, right? So detailed design, as I said, you focus on the particular area so that you can actually collect very specific information. That if you have to do a stability and seepage analysis, we collect the particular foundation condition under the dam and also hydrological, hydrogeological information for that area. So we will start providing this detailed design work. And usually in this time, we submit our regulatory approval submission document, as well as we prepare IFC drawing, which the client use for the specification and the bid package for tendering and etc. But the important thing is that, as we all know as an engineer, the devil's in the details, right? So this is the most challenging part of the project where we really have to understand all the details and evaluate the risk and come up with an optimized design. So going back to the same example, the project that I used as in the Bow River Reservoir option for the feasibility, that project is not it should be awarded for detailed design, but it's not there yet. So that's why I picked up that other projects that I'm involved is the Springbank Harvesting Reservoir. So Stantec was the consultant who did all the detailed design for this structure, and I was able to look at the report as a part of the risk assessment that we are doing last couple of years for this site. So it's a pretty complex structure. So this is the Bow River, and then they put a diversion structure here, which is a concrete and electrical mechanical structure. And the idea is that during a big flood, when there is Albo River Valley is full, they'll open this diversion structure and they cut a diversion channel, this yellow, and then they will start diverting the water so that instead of all this water getting into the into downtown downstream into Glenmore Reservoir and then into Calgary, city of Calgary, we're going to divert and create this reservoir. So we build a around 40-meter high dam, and that dam will be holding this water that will be diverted. So it will hold this water until the peak of the flood is passed, and then after the flood attenuated over a month or two, I think slowly the water will be released into the Elbow River. So it will essentially act as a dry dam every time when there is a big flood. It will be activated, and the water will be stored temporarily, and then it will be released after the flood is over. So in the design stage, I think given the complexity of this, all the detailed design for all the elements, right? Diversion structure, which it has a control structure, gates, and all these things was designed, and emergency spillway. It has emergency spillway. It has a service spillway in the main river. So all these details was designed, and the construction drawing was prepared, as well as the instrumentation plan, because instrumentation is a big part of dam surveillance and monitoring. And then going back to this Opta that I was involved, actually in the detailed design state, as you can see from these things, we actually developed the complete detailed design for construction. We identified what kind of slope is needed, and then what kind of material is needed, what is the zonation, and then what are the seepage mitigation measure, and then surface water mitigation measure, and the groundwater mitigation, all the ditches and channels, as well as all the groundwater pumping well, just to, because as I said, it's a pretty large structure, so it has a lot of components. So all these details was developed. The next step is the construction. Once all this is being done, the construction is basically starts with contract award and then site preparation, which usually takes some time, and then procurement and construction. And then once we start construction, we study instrumentation as well, because that way we know whether our design and our construction and performance is on par, or we need to make some changes to the to our current design. And then at the end of the construction, we do as-built or record drawing. And then we also need to test everything in the dam before we commission it. But the important thing for the YP is that, always take the opportunity to go to the site because it gives you an invaluable experience because nothing matches the field experience in terms of your learning and education. Like a lot of things that you learn in the classroom, but you can see how that unfolds in the field. And that's where the real learning begins. So construction could be very complicated. I think for the sake of time, I'm probably not going to go over a lot of this. I mean, what I was hoping to say that, for example, if this is a zoned earth, you have to build very carefully all these zones, and it needs a very careful construction methodology specification as well as construction control. And that's a big part of, our job as a geotechnical engineer or dev engineer. The last few slides I have was actually the commissioning. Commissioning of the dam is also very important. So you are done building your dam, and you done all the ancillary structures, everything. Now you need to fill it, right? So the filling could happen either by diverting water from the nearby water source, which could be reservoir or river, or it sometimes some facility needs several years because it collects water from the rainfall, runoff, and all these things. So it could happen in one big infilling, or it could happen in multiple years. But whichever way it happens, actually, this is usually the most critical phase of a dam because this is when the dam is actually exposed to its full loading, right? So if there is any major deficiency or anything happens, that's when it's going to manifest. And if your facility can survive this first infilling, and then if you can continue to monitor, which is the next part of its life phase, then you know that you have a safe and sustainable dam. This is a photo from one of the very known uh, failure happened in USA in 1976. Teton Dam failure. It was designed with the state-of-the-art technology at that time, but it did fail right after the first infill, and it actually instigated a lot of changes in the dam practice in North America. Anyways, the operations is another big part because, as I said, that we operate the facility for many decades. So operations could be reservoir level management during flood, supply, irrigation, power generation. So it's almost like 24/7 work, or at least a routine work. And then we also need to inspect and monitoring. We have to maintain the equipment. And then the other thing is, of course, the important part is the emergency management because all dam has designed for certain capacity. As soon as that we have a hydrologic event or any internal or external hazard that impacts that or that goes over that design capacity, we will have an emergency. So we have to understand the emergency. And then the environment and regulatory compliance is a continuous thing, right? Because all these practices and understanding evolves. So the dam that is built 80 years ago still need to meet the current regulatory and environmental compliance. So that could be additional work to that. And finally, the documentation and reporting is a big part because we have to document and report so that we can maintain the knowledge learned for this structure. What else? Yeah, this is just some photos from some of the projects that we did. This is an standpipe geometer. This is an emergency exercise that Alberta government did, and this is our team working on a dam. This is just to take a measurement of the repair. Some of the projects that we did, I think, where we looked at very closely the instrumentation and the regular monitoring or periodic monitoring, and it's a big part of operations of the dam. And finally, this is the last slide. The project that I showed, the Opta, this is I'm not involved in this project, but you can go into the Google and you can see. If you recall this is the boundary, right? This is how it looks like after it is being constructed. Now it's in operation. So this is my presentation, and I will stop here. And if you have time for questions, I will be happy to answer some questions.
Excellent. Thanks for the presentation. Yeah, if there's any questions, you can put it in the Q&A box and I can read them out. I guess I have a question from listening to that. So what do you think is going to change the most in the next 10 to 20 years? And over the course of your career, what's changed in terms of uh, dam design? And,
Yeah, good question. So what's going to happen in next 10 to 15 years? Um, One thing is that, as I said, that like in North America, we're not building as much water dam that we had done in 80s and until 80s, right? But we are building a lot of mining dams. But we need to manage all the dams that we have constructed and maintaining. These are big part of our social and economic uh, condition of countries. So we will continue to need a lot of engineers, young engineers, to come and understand the dam safety, dam design. So that's one thing I think in terms of the how the industry is going to evolve. We're probably going to focus more on the in the water dam side, on the management of the existing structure, and the mining dam side or the industrial side, we're going to construct and manage lots of facilities and dams. So that's kind of one part of the his of your question. And then the other part you said that what's going to be big change. That is the change is that in the mining industry there is a big change going on. Some of you guys might have heard it's called GSTM. I think they come up with these global standards. So mining companies are working very hard to comply with that. So that's driving a lot of changes and a lot of work for the dam engineers in general. Um, but I think in terms of the i- design changes or technological front, I think there's a big advancement. I think we understand a lot better now, how this dam operates because we have a lots of knowledge about the dam performance and behavior over the last 100 years. And automation, I think a lot of this dam instrumentation and monitoring, a lot of automation is happening. Um, and then I think we're trying to implement, modern technology as much as we can. But there is a still need for this fundamental knowledge about how dam are designed and constructed that still need to be understood. And that's something that young engineers should get under their belt.
Thank you. I guess another question I'd have is, do you think empirical correlations like your SPT or CPT based charts and all those are kind of used too often? And are we overfitting these kind of complicated models to data that isn't very complicated?
Um, it's a good question. I mean, there are two ways to answer this question. Number one, from the technology side, as I said that, we used to do simple slope stability model. We used to do simple site characterization. There was only a handful of data, and we just did some rudimentary, lab testing, and then we used correlation, right? But now we have the ability to do some high-end modeling as well as in terms of site investigation. We can use CPTs, and then we can also do, I mean, more in situ data can be collected from CPT, but then we can also spend time on doing some more advanced testing. So in terms of developing the geotechnical characterization, which I call for the foundation or the dam material itself, um, I mean, the current state of the art technology is quite mature, but the problem is that the second part of the question that I answer is that it always depends on the how much resources you have available and the complexity of the structure, right? If you're designing a very complex, very high consequence structure, then definitely you have to um, spend a good amount of effort to characterize and then understand it and so that's must be available to do that and that happens in most cases. But if you don't have if it is not a very significant dam and you know a lot about foundation and etc., then I think you probably take a slightly different approach.
Okay. Another question here from Frank. So you mentioned instrumentation briefly and seeing piezometers and settlement plates and inclinometers used quite a bit, but do you see kind of different instrumentation such as fiber optic tensiometers being used more? And
Yeah, so the standpipe piezometer is the oldest piezometer instrument that is being used, and then come the slope inclinometer, and then now we use shape accelerator and some more advanced version of these. And then in terms of standpipe, we use vibrating wire. And then I think the questioner mentioned that optical fiber, that those are being used already. Like Europeans are ahead of it, and we're trying to specify those some of the newer dams. The industry is quite open, and I think in the mining dams, I think some of our projects they are going as far as using microseismic seismic monitoring system, like they're embedding them. So in this day, like most of the dam owners are very open and they wanted to know what kind of advanced technology they have that is available in the market, and they do consider those very seriously. The other part of the instrumentation process is the automation, right? We try to get to a state that almost like an industrial setup, right? You have all the bells and whistles, and you sit in front of a monitor and you can monitor the dam, right? So that is the expectation of a lot of the large dam owners, and they are actually putting a lot of effort. So yes, the answer is that any advanced technology anybody can use, and if they come and talk to the mining company, sorry, the dam owner, either water dam or mining dam, they will be very open to entertain and integrate that in their project.
all
Somebody
right.
raise hand. I don't know. People
Yeah.
can answer question.
Um,
People can ask question. Sorry,
see if I
Dennis.
can unmute.
Maybe you can put your question on the chat. Question and
Yeah.
answer. If you wanted to ask me anything.
Okay,
Yes,
so
I
last
see.
question here I got, yeah, it's what is the outlook for dam professionals in Canada? Is the industry facing a potential labor shortage, specifically regarding young dam engineers entering the field?
Yes, I think I'm glad that somebody asked this question. And yes, there is a huge shortage of them. I think I was having some conversation with the water dam folks yesterday actually, and we're just going through all the potential projects that are in the pipeline, and all the other rehabilitation projects and etc. Plus, I think a lot of the, as I said, that the major dam construction and the wave was in 70s, 1670s, 80s, right? A lot of those people are now going to retire. So there is a bit of a generational gap. And then on the mining side, it's even worse because mining side, they are now getting into what we call EOR framework, right? You need an engineer of record for each mining dam facility, and which needs a handful of people under each EOR. So there is a acute shortage of young engineers. So yes, engineers, if you guys are interested to come into dev industry, you have a bright, at least, and if you stay focused, I think you will have a good career. What is the next question?
I think we're all good on questions. Thank you
Okay,
very much.
okay,
That was very informative. It's great.
okay. Thank you, guys. Thank you for taking time to attend this. Bye bye.
Bye now.